Okay. A reinforced concrete circular section of 50,000 mm squared cross-sectional area carries 6 reinforcing bars whose total area is 500 mm squared. Find the safe load the column can carry if the stresses in the concrete is not to exceed 3.5 megapascal. So they have given us the stress in the concrete is 3.5, and then they have given us the ratio of the Young's modulus based on E steel to E concrete. That means Young's modulus for steel over Young's modulus for concrete. So that means ES over EC equals to 18. So the total area of the concrete, reinforced concrete of the circular section, the total area of the circular section is 50,000. This is the total area of all the 6 steel rods. So therefore, first thing is we have to find out the area of the concrete, because we have got the area of the steel rods. We haven't got the area of the concrete, okay? Because this 50,000 here is not the area, cross-sectional area of the concrete. So you have to look into 2 different materials. So that is why you have to look into each material separately, okay? So that is why you have to find the AC and the AS as well. But then the AS is given, the total area of steel bar is given. Okay, so this is the questions. This is the reinforced concrete column. The pink color is the concrete and the blue color is the steel rods, okay, are the steel rods. So the area of the concrete circular section, that means you have to find the shaded ones that is in pink color, okay? You have to find the cross section of the concrete that is shaded in pink. So you have to take the total area of this circle, the total area of this circle, that is 50,000, minus the area of each individual small circles here. That means minus of each individual blue circles here. Okay, so the total of all these, you add up all the blue circles, they give you 500. So to find this area here that is in pink, okay, so you need to take the 50,000 minus 500. So you've got the area of concrete, that is 49,500 mm squared. Where the area of the 6 reinforced steel bars, reinforcing steel bars is 500. Okay, so now, first we have to remember what we have studied earlier. Young's modulus, we know Young's modulus is defined as stress over strain. Okay, and strain is defined as stress over Young's modulus. And also strain is also defined as deformation. Okay, deformation over original length. Strain is defined as deformation over original length. Young's modulus, now this is uppercase letter E, yeah? This is epsilon. So you must be able to differentiate the two. So this is Young's modulus. Young's modulus is defined as stress over strain. Okay, if let's say, for example, you want to take strain to be the subject, then you will have stress over Young's modulus. And we also know that strain, the direct strain here, epsilon, is defined as deformation over original length. So if we equate both these equation here, if we were to equate both these equation, okay, we have x over L equals to sigma over E. Okay, we will have x over L when you substitute this, which is the epsilon here. So you will have x over L equals to sigma over E. Okay, then since for parallel bars, this is considered parallel bar. Since for parallel bar, the deformation is the same for the concrete and the steel. Okay, the deformation has to be the same. So therefore, okay, you have this. Okay, because if let's say you equate this with this, you equate this equation here with this equation, you will have X over L equals to sigma over A. So changing only X to subject, then you have to bring your length, original length, over to the right-hand side. So you have sigma L over E and sigma L over E. So that's for concrete, and this is for the steel. So if let's say the length of concrete, this length here of the concrete is equals to the length of the steel. If the length of the concrete is equals to the length of the steel, you will get an equation like this. Okay, sigma over C over EC equals to sigma S over ES. But the length are equal, so you can strike it off. Length C LC, strike off with length LS. So remain sigma C over EC equals to sigma S over ES. Usually their original length are the same. If the original length not the same, that will be given in the question. So usually we practice the same length, but the deformation, okay, for parallel bar is standard here. Okay, so if the length are the same, you strike it off. You get sigma S over ES equals to sigma C over EC. So changing, okay, sigma S to be the subject, then you will have this equation here. So why do we need this equation? Because we want to find sigma S. Sigma C is given in the question, 3.5. ES over EC is given 18. So we can make use 18 here times sigma C, that is 3.5. So you get your sigma S, 63 Newton per millimeter square. 63 Newton per millimeter square, or that is also equals to megapascal. 1 Newton per mm square, 1 Newton per mm square is actually 1 megapascal. So this is equivalent to 63 megapascal for steel. For concrete is 3.5. So we have to find the total load. So remember, we have the formula of this for parallel bar. Total force equals to the force for steel plus the force for concrete. So if let's say, for example, okay, you can replace this force here, the force by sigma S times AS, and the force for concrete by sigma C times AC. So we have known sigma S, AS, we have known the sigma C and the AC. What we need to do is we just substitute the values, we can find out the total force, 204.75 kilonewton. Okay, that's for this example.